Hi, my name is Mateusz Dular. Good afternoon or morning or evening or wherever you are. Unfortunately, we cannot be in Korea right now, so I found the second best place in the world, I guess. And I'm here to tell you about the Kelvin-Helmholtz instability, which we found in cavitating microchannels and what importance do they have. So a little bit about motivation for this work that we did is actually it comes from a completely different perspective. What we're doing from the last couple of years is we're trying to use cavitation to clean water from viruses and bacteria and so on. So this is kind of an exciting time for us because we also work with COVID or coronavirus, and we're trying to disinfect wastewaters with it. And as you can imagine, then if you want to know what is really going on with viruses, you have to scale down your test section to a very small volumes. So what we're doing, we're having test rigs developed which go down to maybe a couple of milliliters, so that they are not endangering the operators which are working with these samples. So our typical setup looks like this. It's pretty much a normal cavitating channel. So we have a pump, we have a filter because we don't want to have small dirt in our microchannels. Then you have the simple microchannel and a closed loop, of course, and then we have also a bypass by which we can regulate the flow rate through our section. So a typical geometry that we have is a 18 degrees convergence angle and 8 degrees divergent angle Venturi channel. The height of the channel goes to about 1 millimeter and less, and then we have the width of the channel from 45 to 75 microns. The conditions, yeah, they go from 2 to 12 bar and to about 70 meters per second. And this particular work that I will show you today, it applies to all range of conditions that I've discussed. It actually is on the 675 micrometers high and 450 micrometers wide channel. It's 7 bar at about 40 meters per second. The flow is turbulent. Okay, and we have cavitation number of about 0.785. So what are the general observations? What we can see in here? So it's quite small, right? So this is about 1 millimeter here. So we're looking at cavitation pocket, which is about 5 millimeters long. And what you can see is a single attached cavitation bubble. So it kind of resembles the supercavitating bubble in this case, but it's not stable. Then we have very small shaded cavities. Then we have the Kelvin-Helmholtz instability here. And finally, what we don't have is an absence of shock waves. We don't see shock waves, which is kind of surprising. And we should have seen shock waves, because we developed some methods lately which enable us to visualize it, like this one. And we're also using a very fancy visualization method by illumination by femtosecond laser long pulses, and we should see the shock waves if they are there, but they're not there. So to go a little bit more into depth, so what does cavitation dynamics looks like? So we have this stable cavitation pocket. Then we have instability developing in here, and this instability actually moves forward. It looks kind of similar to the condensation shock which was observed by previous studies, right? But it does not disrupt it in this way. It actually grows into so high that it disrupts this area here, and you have very small shedding or very small cavities in this area here. So this is actually what is going on. It's kind of hard to see. So what we were able to do later, we were lucky enough to be able to go to Aragon just before the pandemic broke out. This was in November of 2019, and we could use X-rays to see the same thing in their setup, right? So what we see here is this is liquid water. This is completely vaporous pocket, and this is a very straight line which is interface between the liquid and the vapor, right? So now you can see the instability growing. It goes quite high here, and slowly it starts to disrupt the closure of the vapor pocket. And in final case here, we have complete disruption and collapse of the cavitation pocket. So there are people who noticed this before us, right? For example, Paul Brenner saw it, but they never, so he saw it on a macroscopic spherical object, right? But they never associated it with the global behavior of cavitation. So that's something new. So basically what we are seeing here is this, right? First you have growth of the stable cavitation pocket. At number 5 it stops because of the pressure rises too high in this region. Then you have the shear flow between the liquid and the vapors, which is now stationary, and this is what causes the formation of the Kelvin-Helmholtz instability, which grows. and disrupts the cavity closure line, and you have shedding of the small vaporous pockets, right? And then this repeats, or not repeats, it's a continuous process, right? It moves upstream until number 15, where you have again the surface tension forces which are strong enough so that this vapor pocket is now stable again and begins to grow again, and the process is repeated, right? So it's a little bit different, and it's actually the third mechanism of cavitation cloud shedding which was observed until now, right? So the first one was re-entrant jet, the second one was condensation shockwave, and now the third one, in very specific conditions in microchannels, you can have this Kelvin-Helmholtz instability which drives the global behavior of cavitation. And you can make a very simple model to prove it. So the model basis on Bernoulli equation, so it's a very simple model. So we have the interface which has a small disruption. In the model we used an initial disruption of 1 micrometer. You have two streams. One is the liquid stream, the vaporous stream, right? They have different velocities, and then you have the height, which is a function of the position and the time, and then you have this shift of the layer, right? And what you do, I won't go into the equations. If you want, you can we can discuss them later. So you have basically the balance of forces, of the gravity, of the surface tension, of the viscosity, which are very, very small. And then the driving force is actually this delta P, the difference is in pressure, which is actually the function of how high this interface is, right? So this is the main parameter here. And then you can, from this, you can calculate the rise, the acceleration of the rise, then you can calculate the velocity of the rising interface, and of course the displacement. And a very simple condition is how the shift occurs. It's basically just what's the difference between this velocity, and this causes this shift delta actually. It's like this, right? So it's a very, very simple model, but it produces really nice results. So we compared 3 different conditions for the microchannel, which is the one that I've shown you here, right? So we have this height and width of the channel and the velocity, and these parameters are the same for all 3 cases. Then we have the millichannel, which is considerably larger, but it's already in a millimeter size. So this was the work that we've done almost 10 years ago in Lille with Olivier Coutier. So this is one. And then we have the microchannel, which is actually a 10 by 10 millimeter channel. And it's a big one, right? So that's 5 years ago. And now we're comparing what happens if we put into these parameters into the model that I've just explained. So in macrochannel, you don't see much, right? So this is the time, this is how it starts, and then it goes to about 1 millisecond here, right? And you can see that the instability, it's there because it's a perfect system, right? And it grows, but it's not significantly high, right? So this bluish plane here actually estimates how deep would the re-entrant jet or the shockwave penetrate if this would be a normal sized channel, right? So you can see that the re-entrant jet or the shockwave will be considerably more important in this case than this Kelvin-Helmholtz instability. If we go to milli channel, already you see that there is a significant waviness, but you don't have this shift, the roll up, which is important for the disruption of the whole cloud, right? And finally, if we go to the microchannel, you see that the roll up now is significant compared to the penetration of the re-entrant jet or the shockwave. So we can claim that this roll up, together with the Kelvin-Helmholtz instability, is the cause for cavitation shedding mechanisms in these channels. So to conclude, so yes, we found that it's present, Kelvin-Helmholtz instability, in cavitating small channels. What is more important, this was already known, but what is more important is that it can govern the cloud shedding in cavitation microchannels. And it's only the third mechanism of cavitation cloud shedding, besides re-entrant jet and shockwave. And we also developed a simple model which basically has shown that this is so. So I would like to thank you. First of all, I'll thank my sponsors, which is the ERC, which is sponsoring my research lately, the national agency, and this particular work was also sponsored by the Alexander von Humboldt Foundation. If you want to find out more, hopefully you'll be able to see this paper in Journal of Multiphase Flow. It's been in review for quite some time. And if you want to chat or have coffee or beer, I'll have my Zoom channel open after the CAV meeting for 1 hour, and we can talk about anything you want. And if you want to contact me, these are my details. So have fun, and I hope to see you in person really soon. Bye-bye.